let's apply the calculus for computing the circumference of a circle. To do that, we first need to talk about how to compute the length of a curve. We call that the arc length. So here is some arbitrary curve that I call gamma. It may have a functional form, y equals y of x. To compute the length of this curve, we look at a small segment of the curve that we call ds and apply Pythagorean's theorem. So ds is part of a triangle which has a dx and a dy in it. So ds then is equal to the square root of dx squared plus dy squared. Okay, so what does it mean to compute the arc length? It means that we're going to be computing by summing over all of these ds's. So I'll write it as an integral ds and say that we're going to sum over all the ds's lying on the curve gamma. So I'll put a gamma under the integral sign to show that we're integrating the ds's over this curve gamma. So in order to do that, we have to represent ds in some way that we can do an integral. So one way of doing that is the case where we have y equals y of x. Then we have dy is y prime of x dx, but we'll use Leibniz notation. So that's dy dx, right? The dx just cancels here. And then we can write ds then as the square root of dx squared plus dy squared. And dy squared now also has a dx squared in it. So it's dx squared plus dy dx squared. So we can take the square root of dx squared and factor out the dx then. So that becomes the square root of 1 plus dy dx squared times dx. So this is a way of representing our ds in the integral sign in terms of some function times dx, and then we can integrate over x from the beginning x to the final x. That's one way of doing this integral. The second way of doing this integral is if the curve is somehow parameterized. That means we can draw the curve in such a way that we can say x is some function of a parameter, which I'll call t, and y is some function of a parameter t also. Then we can find dx and dy. So here dx then, using Leibniz notation, is dx dt times dt, and dy is dy dt times dt. Then our ds, which is again the square root of dx squared plus dy squared. Now each of these terms will have a dt squared in it, and we can factor dt squared and then take the square root. So that becomes the square root of dx dt squared plus dy dt squared all times dt. So now we can integrate over gamma ds by doing an integral over the parameter dt. So let me show you an example. Suppose we have a circle, which is the name of this talk, this lecture, Circumference of a Circle. So we look at a circle, and it will have radius r. And we want to, we can do this in two ways, but I'll leave one way for your homework assignment. And the way I'm going to do it is the easier way, actually, which is by parameterizing the circle. So we can parameterize the circle. We can write x equals r cosine theta and y equals r sine theta. So we parameterize the circle with this angle theta that it makes with the x-axis. So this is called polar coordinates. If we do that, then theta is our parameter here, and we can take the derivatives. So we have dx d theta is negative r sine theta, and we have dy d theta equals r cosine theta. So then we have our ds. So our ds here is equal to the square root of this r of minus r sine theta squared plus r cosine theta squared. So both of them have an r squared, so it's the square root of r squared. And then we have a sine squared theta plus cosine squared theta times our, this is the square root of this, times our d theta, which is our parameter. And then sine squared theta plus cosine squared theta is 1. And the square root of r squared is r. So this becomes r d theta. So ds is just r d theta. So that's very simple, right? So ds, the small arc length here, is just the radius times d theta. You kind of know that already. So then to find the circumference of the circle, then we have the integral over the circle itself, ds. That becomes the integral of r d theta. And we need to know how do we get the whole circle when we vary theta. We get it when we vary theta from 0 to 2 pi. So this integral becomes from 0 to 2 pi of r d theta. R is just a constant, so the integration is r theta. The lower limit is 0, the upper limit is 2 pi. So this becomes 2 pi times r, which we all know is the circumference of a circle. So a rather trivial example. You can do it the hard way for homework, but this is just to illustrate now the power of the integral and calculus to find arc lengths. And here we find the circumference of a circle. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.